I'm Professor Angela Beck. I'm an associate professor in this department, and tonight I'm going to tell you about what the zodiac really is. Now, in order to do that, we actually have to do quite a bit on how we see the sky. What is it that we look at when we see the sky? So, I'm going to start by just describing how to look at the sky, and we need to talk about a few different ideas before we can understand some of the things that have been in the news in the last couple of months. So some of you may have heard that the zodiac signs have changed, that there's an extra one, that sort of thing. And so I'm going to explain to you what that's all about. Okay? Now, in order for me to explain this, we have to think about how we see the sky. And there's this ancient model of how we see the sky, which is called the celestial sphere. It's kind of like how the ancients thought of the Earth as being a stationary thing, and the heavens are an entity that moves. Now, we know that this is not true, but it's actually a convenient way to think of how the sky looks. If we think of it this way, we can actually use it to think about, well, what should we see where? So the celestial sphere is this construct. It is an enormous sphere, which we are in the middle of. There is a pole to the sphere, which is directly north of the North Pole and directly south of the South Pole. And there is an equator, which is just the extension of our Earth. Okay? So this is where all the stars are. All the stars are embedded on the inside of the sphere. Like I said, it doesn't really matter that this is not true. Think of this as being like a map. When you use a map, you know it's not real. It doesn't have hills, it doesn't have curves of the Earth, but it lets you find where you need to go. That's kind of what the celestial sphere is. It allows us to think about where things are connected in time. Okay? Now, we need to think about how this looks from different places on Earth. So I'm going to talk through this one. Here we have the Earth, and the North Pole is up here, the South Pole is down here. There is a man standing at about 35 degrees north to south. What you see here as this plane is his horizon. That is to say, he looks out and he can't see below that. That is where the horizon is. So that is this plane that you can see here. He can see all the stars up above the horizon. He can see none of the stars below the horizon at a given moment. Okay? But this sphere is turning around. Remember that the Earth turns, so the sky appears to turn. So our celestial sphere is turning around, and so you have this thing that's going around and around. And you'll have some stars down here that you can't see, and they will move up and go over the top and come back down. Stars rise and set, just the same way if the sun rises and sets, the moon rises and sets, and for the same reasons, because the Earth turns. Now you'll notice that there are some stars in here that actually as the sphere turns around, they never go below the horizon. They're always up. So no matter what night you go out, you will be able to see those stars. Okay? And we'll talk a little bit about what those are. There are also some stars down here that you will never ever see. They are always below the horizon. If you want to see these, you're going to have to go down into the southern hemisphere to see them. Okay? And we'll talk about why the buildings don't go to, because it has to do with one. Okay, and so we have this idea of this celestial sphere, and actually there's a star right above where the North Pole is. So if you are stood at the North Pole of the Earth, and you look directly above your head, there's a star there. It's called Polaris, or the pole star. And because the Earth turns, because the celestial sphere appears to turn, what you get is that the pole star stays still, and everything seems to move around. Okay? And so seems to have frozen. Hang on. Oh, I really have frozen. Oh. Okay. So this is an animation that I'm going to show you, and I need to introduce what's going on here. I may turn the lights right down just so that you can see. On the other hand, I may never get them back up again, so I might not. This is the pole star, this one that's marked right here, and these are other stars in the sky. This is actually the date and the time, and this is the location. So this is assuming that you're in Columbus, Ohio. Columbus is a little north of us, but not by much. So it's a pretty good representation of what you would see if you looked north on the right day of the year. And you would see the pole star. You'll see the pole star if you go outside tonight. And we're going to watch what happens over the course of a few hours. And so hopefully you can see this. If not, I will give you some light to make it really dark in here. You'll see that everything is turning around. The pole star stays still. These things are going around and around. Some things are going below the horizon. Some things are coming up above the horizon. So the point is that if you actually watch the sky, which most people don't do these days, if you watch the sky, you will see that the stars move around over the course of a few hours, that the pole star stays more or less where it is, but other stars go around, some set, and some rise. Okay? And so this is showing you how the celestial sphere appears to move. And so this is how ancient people saw the sky as moving and modeled what they saw. Okay, and so I have a picture here that's a static picture, and this is what happens if you take a picture for about the same amount of time. So if you set up the camera and you let it take light for a few hours, you will get a trail that is, as the star moves, it appears to be in a different position, and you will see a star there. And so you will get something like this, where the pole star is actually this little arc here. It does move just a little bit. It's not exactly at the North Pole. It's offset by just a tiny amount. And you can see all of these things go around. Now, one of the things that this then allows us to do is we can use this for navigation to some extent. So back to our usually large man, stood at 35 degrees north. Now, if he looks directly above his head, he's actually looking up here, right? So if I'm stood outside and I'm looking up, I'm not looking at the pole star, I'm looking directly up. I'm actually going to see stars go over the top and disappear. So I'm going to see different stars at different times. If I want to see the pole star, which is over here, I have to look that way. I have, no, it's not that way. That way, I did sorry. Anyway, so what I'm going to have to do is actually, it's going to be somewhere up here, okay? And some very simple geometry will show you that if this is my horizon, and I look at the horizon and I want to move my head up by a certain amount to see it, I will have to move my head up by the same as my latitude. So actually the pole star, for people in the northern hemisphere, gives you an idea of how far north you are. I grew up at 54 degrees north, which is significantly further north than here. And so I was used to looking further up on the side to see the pole star. Okay. Now, in terms of what you see at different latitudes, this is really important. So these are basically, let's just concentrate on this one for now. What we have here is, this is someone who is at 45 degrees north. So this is their horizon. This is what they can see all the stuff above. They can't see anything below this. As the celestial sphere turns, you can see here, there's the star Castor, which is part of Gemini, that goes around, and it's actually above the horizon on this particular day for most of the time. So for most of the time, you can see it. Whereas this star down here is above the horizon for less time. The North Pole star is up here. If we move further north, 70 degrees north, that's now inside the Arctic Circle, that same star, Castor, now is a certain polar star in their set. It's always up there. Whereas this one that we can see some of the time, Sirius, is now very noticeable. You have to look right to the south. And it will only just be above the horizon for a very short time. Okay? If you're at the North Pole, nothing rises and goes around and around and around. The North Pole star right above your head. Okay? But if we then go to the equator, we have the opposite point of view. Everything rises and sets. Okay? You can see these stars for exactly half the time. Half the time they're below the horizon, half the time they're above the horizon. Okay? And this is actually one of the many reasons that we tend to build telescopes within the tropics, because from there we actually can see all stars. Okay? Some of them are still going to be low on the horizon, but from within the tropics we can see everything. And so it's a much better location for building a large, expensive telescope. There are other reasons why we build it in Hawaii, not just you can ask me about that later. So hopefully you get the idea of, depending on where you are, you'll see everything. From here, you're looking at something, it's a little bit like this. We haven't actually talked about what our latitude is. Yeah, we're actually about 40 degrees north, so we're a little south of where this is. So we actually see the north stars, whereas at the North Pole, you only see one. Okay? Now, I want to introduce the idea of constellation. Okay, that's really dark. So I'm just going to switch the light off for a second. It's going to get really dark in here. Small children, don't get panicky. Okay. Okay. So what you're looking at here is basically a map of the sky at a certain time of year, and I'm going to put the light back on so that we don't get too sleepy. And what's overlaid on that is this idea of constellation. So basically, if you look at the sky, there's a whole bunch of these dots around it. And then we use constellations as a way of remembering what stars are, or what they're encountering that they be. Okay? So in this particular case, which I'm not going to dwell on since it's a little too dark, the North Star is right around here, and you've got everything going around and around that point. Okay? But the constellations there's no physical relationship between the stars. They're just, hey, here's a pattern of stars. This is what we see. Okay? So this is one of the constellations, one that we can see. It's actually a circumpolar constellation from here. This is the one that you're probably most familiar with. I call it a cloud, you guys call it a big dipper. It is actually not a constellation, it is an asterism, it is a piece of the constellation. But it's part of this thing that is thought of as being there. It also helps us to find where the poles are. Okay? I'm going to come back to this point, but there really is no physical relationship between these stars. They just happen to be in the same direction. Okay? And to try and demonstrate this, let's say I can perceive death, in part because I'm used to standing around in places, and in part because I have two eyes. Okay? So I can tell that this guy is in the front, and you guys are in the back. Okay? Now, what am I choosing? Where's that? And this guy's in the front. If I can perceive that, the distance between them would be incredibly big, right? And that's what's going on with the stars. They may be at very different distances from us, but they're in the same direction. Okay? And we'll have a look at that again shortly. This is just another view of that particular constellation, in part because it shows you the relationship between, this is the great band as a major, and the little band as a minor. This is the pole star, and this is how you find the pole star if you're a pole control. Because it may be helpful sometimes. Okay, and then I wanted to bring up another constellation that most people are familiar with, and that is Orion. And again, you have different people who will always mention different. But we have these four stars that are very bright, and then the belt, and then the sword. How it looks without the drawing on it is something like that. Actually, we would not say, look, anywhere near that nice in the long area, because the light pollution is too bad. You can't see all of these nice background stars. But you can make out the main star. This is Betelgeuse, which is the brightest star in Orion. This is Rigel, the second brightest. Here's the sword. And in fact, this blobby bit here that looks like a star is not a star, it's a nebula, so there are lots and lots of new stars and planets on it. But this is one of the most famous constellations. And one of the reasons that it is Orion has to do with the idea of telling stories to remember what the constellations are and where they should be. So actually in the sky, it is chasing, depending on which version of the image you look at, it is chasing either Taurus the bull, it's a hunter, it takes a bull, or it's chasing the Pleiades, which is actually one of the great myths that he's chasing the seven sisters. Okay? But it is a way of using stories to remember this is where the thing should be. So Orion is about, when is this hunter going to come across the sky, and over the course of the night he chases either a bull or women across the sky. Okay? Now, this is just another point of view on this. So here we have again Betelgeuse and Rigel and some of the others. You can see there are very different distances. Betelgeuse is about 400 light years away, whereas Rigel is twice as far. And Pentaca is almost is a little further than Rigel, and so on. And so we have all these stars at different distances. There really is no physical relationship. They just happen another graphic to try and make sure that we get this idea. So this is kind of showing you how far away they are, and then this is how they look to us because they happen to be in the same direction. Okay, so we've introduced the idea of constellations. I'm going to come back to that. Historically, the idea of constellations was just, oh, this comes out, and it's a story that I have. Now, the next thing we need to think about is, well, how does the sun fit into this? Your zodiac sign is supposed to be about where the sun is on the day you were born. Okay, as you have to know you were born. And so you have to be able to think about where the sun is. Now, we know that the Earth goes around the sun. But you can put it into this model of the celestial sphere, the stars are moving because the sphere is moving. And the sun is also moving. And over the course of the year, on a given day, it's basically at one spot in the celestial sphere. So as the celestial sphere moves, it rises and sets. But it moves just a little bit each day. Okay? So over the course of the year, it moves across the celestial sphere. Now, you know that you don't, the sun doesn't appear just anywhere. It's going to, right in the east, be in the south of the moon, second west. In terms of where it would be with respect to the background stars, we can't see the stars during the day, the atmosphere is. But if we can see them, there will be stars all over the place, and there will be some stars behind the sun. And it isn't bounded up here and over there and down here. It's bounded in a very small area of the sky. And so that is what this represents. It's called the ecliptic. In the term of constant eclipses, the moon is also a different place. Okay, more or less. And so over the course of the year, it follows along this path. And you can see that it's not the same place as the celestial equator or the equator of the Earth. This is important for the way in which we're looking at where the sun will be with respect to the constellations. Now, I'm going to show you another video. What this is showing is, if you could either get above the atmosphere or just look at the sun without the atmosphere stopping you from seeing the stars and without destroying your eyes. This is what you would see over the course of the year for where it would be with respect to constellations. Okay? And I will show this more than once. Okay. So it's starting out as in Virgo, and then it goes through Libra, etc., etc. It's going through all of these constellations, and it basically doesn't end up here or down here. It's only going through a small number of constellations. Okay? And I'm going to show this again, and I want you to pay attention to this spot and this spot. Okay? But over the course of the year, it goes through the constellations, and hopefully you'll see this one is going back and forth, and this one is going back and forth. What do you think those are? Yeah! That's Venus and Mercury. They're always more or less in the direction of the sun because they're closer to the sun than we are, and so they appear to go across over the course of their period of orbit. Okay, and so this is a more realistic view of what's actually going on. Here's the sun, here's the Earth going around the sun, and if you were able to see the stars, for instance here in September, the Earth is here, the sun is here, the stars behind it are different, right? In June, the stars behind it are different. What that means is that on your birthday, you cannot see the constellation that is your star. It is on the other side of the sun. Right? But actually it's not, because it is, but it's offset a little bit. And we're going to get into it exactly later. Okay, so basically what you've got is, let me just back up a little bit. What you've got is that the Earth is moving around here. So from the point of view of, if you're on the Earth and you're looking at where the sun is to the celestial sphere, it appears to move every day just a tiny bit for the direction that you're looking in towards it. So it will appear to move through just a little bit of the constellation. And it's about a degree a day because it takes a little over 360 days to go around, for us to go around the sun. So the sun will appear to move by just about a degree a day. And so what you've got is, over the course of the year, it will go through all of them, but it takes about 30 degrees for each one. They're not actually even. You can see they're not even. This is where the new sign is. We'll come back to how that ended up there. But this gives you the idea of how we're going around and around. Okay? Now, I want to make sure that we're getting this, so I'm going to make you join in. And I'm going to make you give me your answer with your organic results. Okay? So this is, basically, I have a question that has letters, it's A, B, C, D, so it's 1 is A, 2 is B, and so on. Okay? And so this is my question, and I'll read it out to you. I have this picture of the horizon looking south, and if you can see the stars, these are the stars that you will see, and there's the sun. So, if you can see the stars during the day, this is what the sky will look like at noon on a particular day. The sun is near the constellation Sagittarius. In which constellation do you expect the sun to be at sunset on that day? You have to want to give me an answer. I'm guessing that those of you that are already saying this are, see, just quite a few of you got the right answer. Okay. So we have a difference of opinion. Most of you have got it right. Remember that the sun basically stays in this constellation over the course of one day. And in fact, it takes 30 days for it to get from here to here, and another 30 days to get from here to here. The sky moves. The Earth turns to the sky is moving. So at sunset, all of it is moving down here. It's down there. Okay? Okay, so someone can just yell this one out. What time of day is this?
Alright.
It's morning. That'll do. Close enough, right? Okay, now, give me an estimate of the time on this one. Yes, early to mid-afternoon. Okay? Okay, now then, this is the important one. Are these the same day? Feel free to check out. Well, that's right. Remember that the sun rises in Cancer, it's going to be in Cancer and sets. The whole lot goes over here. Likewise, if it's in Aries, the whole lot is going to move. It's still going to be in Aries. So we all get about what constellations are and how so on. Okay, the next thing we need to understand is why we have seasons. This is actually a really critical part about why we have the current, I hate to say controversy, issue with astrology and zodiac. Okay, so we need to talk about why we get seasons. We get seasons because of the tilt of the Earth. And it's actually to do with how high is the sun in the sky. And I'm going to try to do this as carefully as I can. This is basically the idea that in summer, the sun gets much higher in the sky, and so you have it coming down to a steeper angle, so you get more of the light concentrated. In winter, it's coming at a shallower angle, and so it's not as concentrated, it's more spread out, it's not as effective. I'm going to try and demonstrate it. So I have this laser pointer. When I press it, it gives off some light, right? And if I do this, I have all of that light concentrated on the spot. Okay? Now, if I do, see if I can make it do this. I don't know if I've got steady enough. Maybe you can see that, right? Do you think it's giving off more light than it was before? But it's now spread out, right? And then it's the same thing. The sun, when it's high, that light is concentrated into a smaller spot. When it's low, it is spread out. Okay? And so this is what we call the seasons. But it's because we have the Earth tilted. And so this is basically what we're looking at. We've got, the Earth has this axis that it spins on, but it's not perpendicular to the sun. So this is the sun, and this is the Earth. It spins on an axis like this. And I'm going to show you this animation, that this is kind of a perspective thing, so you can see this axis. At this point, the North Pole is pointing away from the Sun, the South Pole is pointing towards. So you get more direct sunlight from here, it's warmer, and over time that will change. In this top-down view, it's showing you where the poles face out. Okay? And in this side-on view, it's showing you very well exactly what the angle is. Okay? And I'm going to show you how this changes over the course of a year, how the tilt affects what we get in the way of light. So you can see that over the course of time, the angle of the sun, of the Earth's orbit, spin, stays tilted, but now you've got the North Pole pointed towards the sun, and so it gets more direct sunlight. At this point, it's directly perpendicular. That is the fall equinox, and now the north is pointed away, so it gets less direct light, and so lower angle light, and so it gets cooler. Okay? So basically, what you've got is in summer. This is my axis. This is the sun, and the north is pointed towards the sun. This is fall. It is exactly perpendicular. That is, neither the north nor the south is at all pointed towards. It is exactly equal. This is winter. This is spring. Again, back to exactly perpendicular. Now, this idea of equinox, we think of equinox as being, it's the day that we have equal day and night. That's what the word means, equal night. But it's not. It's not actually the day that you have 12 hours of daylight and 12 hours of night. It's the day that the axis is like that. It is the day that the axis is such that neither the north nor the south is pointing towards. It is exactly perpendicular. That is the definition, the astronomical definition of the equinox. Okay. The reason that that's not the same day that you have 12 hours of daylight and 12 hours of light is because the atmosphere interferes. The atmosphere means you can see the sun before it's actually above the horizon, you can see the sun after it's set, and it gets scattered in sunlight gets messed up by direction. So, although you think it was the same 12 hours of daylight, 12 hours of night, it doesn't actually. So, the important thing is our definition of an equinox. Okay, and then this is kind of giving you this from a celestial sphere point of view. So here you've got it from the point of view of, is the Earth going around the Sun? And here you've got the Sun is moving around with respect to the background stars on the celestial sphere. Again, you know this is not actually true, but this is the way that it appears from a celestial point of view. So if the summer solstice in the north, that means it's the highest above the equator. The winter solstice is the lowest below the equator, and the equinoxes are exactly where it comes to be. Okay. Now, why is this important? Well, it has to do with how we set our calendar. Most of you probably think that a year is how long it takes for it to go around the sun. And you'd be wrong. A year is not how long it takes to go around the sun. Well, not the one that uses our calendar, anyway. We use what's called tropical year. The tropical year is set by when is the spring equinox. So when is the axis exactly perpendicular to the direction of the sun. So it goes around and it comes back, and when it gets back to that position, that is how long the year is. And it is a little less than 365 days. But we also have this concept of the sidereal. That is, when does the sun get back to exactly the same position with respect to the stars? So remember, let's say it's in Gemini, and it's got a certain star that is blocking its hiding. When does it get back to that position? That is called the sidereal. It is not the same as tropical year. The difference is about 20 years. Okay? And it is that difference that gives rise to the issues that we have with the solar. Okay, so why are they different? Well, this has to do with something that's happening to the Earth as it's going around in its orbit. Okay? It is called precession. And precession is to do with how the Earth behaves like a top. So it is spinning. So basically it's like this, and it's going around like this. But at the same time, it's very slowly spinning like a top. So it's always got the angle here is always that same 23.5 degrees relative to this direction, which is perpendicular to the direction of the sun. But it's going around and around and around. Okay? It's a very slow process. It's not doing this at high speed, which you needed to do at the spinning ball. But it's going around like this. Okay? But what that means is that you've got the Earth and it's moving around like this, but at the same time it's spinning just a teeny bit. So what happens is that because it's spinning just a teeny bit, it gets back to exactly perpendicular before it's quite made it through 360 degrees. Okay? So that is why the sun isn't quite back where it should be when you get through a whole year. And we say like this today because it actually makes sense for our calendar. Otherwise, we keep having our seasons change. Our seasons wouldn't be in the same months every year. Over the course of time, it would move. Suddenly, over the course of the millennia, you would have spring in June or spring in December instead of March, as we expected. Okay? And so we set our calendar by the seasons and not by actually where the sun starts. So this is basically what that means. So right now, you've got, when you look at from the North Pole, the stuff at the North Pole, you're looking directly north, you will see the pole star. But it's not always there because the axis is moving around like this. And it traces out this circle. Now it takes 26,000 years to do this circle. Okay? So I mean, over the course of 1 year, it's really not a big deal. But over the course of a millennium, it starts to show off. And over the course of the 4 millennia, since the idea of the zodiac was set up to do timekeeping, it has made a difference. So at the time that the idea of the zodiac is a way of looking at where the sun is was set up, actually this star here was at the pole. Then there was a time when there was nothing in the pole, and now we have Polaris. And it's in 26,000 years, it'll be back here. But over time, it's going to be moving around, and we're going to have different stars at that point, directly going on. Okay, so we've got this thing that's happening, and it's over a long period of time, but, like I say, it's 4,000 years since we set up the idea of the zodiac, so things have changed a little bit. And actually, that's added up. There's 20 minutes every year added up. And so now, if you look for where the sun is on your birthday, it's not in the sign that you think you are. I'm a Gemini. My birthday's in June. That means that the sun should be in Gemini on my birthday. But actually on my birthday, it's in Polaris. Because over the course of 4,000 years, it's moved out to Gemini on my birthday. Okay? So what you've got now, the next thing that we have to consider is about constellations. So I said we set up these constellations, but there was never any official kind of, okay, this is this constellation, this is this constellation. Actually, if you look at different aboriginal people, they have different traditions. And so you can find different names for constellations. But even if we go with the tradition that we have in the West, which is mostly the Greek tradition, you still didn't have, this is that constellation, and this is that constellation. But it's kind of blurry where the boundaries were. And so when we saw we found, we have a new telescope, we find a new star, and we describe it as best we can, according to which constellation it's supposed to be. And it has a name according to the constellation it's in. Okay? And the names start with Alpha Orion, this is like star Orion, Beta Orion, and Saturn Orion. And you keep going, and you add more and more letters and more. So, but we realized that, we kind of like to make things official. So, in 1930, the IAU, the International Astronomical Union, decided to define boundaries. But, astronomy is an ancient subject. We've been doing it for a long time, and the data is still useful even from way back then. So we don't want to randomly say, okay, this is where there's this constellation, and this is where there's this constellation. We try to make the boundaries so that we don't have to change the names of those too much. And that means that the boundaries can be a little bit complicated, right? Incidentally, this idea of boundaries and boundaries of constellations is actually somewhat similar to the idea of Pluto being demoted about 5 years ago. That is to say that Pluto is no longer considered a planet, but up until 5 years ago, we never had a definition for a planet because we didn't need one. Because you could always see the planets. And then it became necessary for us to be able to progress in the way we describe things and say, okay, this is what we mean by planet, this is what we mean by dwarf planet, this is what we mean by comet. And so that It didn't actually change anything physical, but it changes how you describe what we're seeing. Okay? And so what you get is something, this is kind of a 3D view where we would be in the center and then you've got these boundaries. And you can see that, like here, you've got this little double bit here, double bit here. And this is to do, okay, there's a star there that somebody said is in that constellation. So let's just make sure it's still in that constellation. Okay? So this is how the boundaries were drawn up. And actually there are some stars where there are boundaries between two, and they have two names that are to do with those constellations. So this is showing you Orion again. So you've got these stars that are definitely in Orion, and so you draw these boundaries around them. And you can see here, here's Gemini, here's Taurus. And there's this little leg of Taurus that goes down here. And you think logically it would make sense to just draw it off there. But these were associated with Taurus, and so that remains Taurus. And we have this official boundary. Okay. This is also...
So like all of these stars that fall in
yes.
Orion have completed part of
yes. So if a star is found, let's say, now we're a very powerful calculus with these two things that you can never see before. Anything that is inside these boundaries is considered to be in Orion. And it will have a name associated with that constellation. Okay? Same is true for any of these boundaries. So here you can see this is showing you another stretch of it. I've got Libra, Virgo, Leo, Cancer. So the Sun would go through Gemini, Cancer, Leo. It would go through here. It would never go through any of these other things. But you can see how here, there's a bit of Leo minor dipping down, right? If that dip was just a little bit bigger, it might actually go through that very easily. Okay. Now, we're going to come back to this. But basically, you've got two things going on. You've got these things now have official boundaries. So actually the amount of time they spend in them isn't exactly 30 days each. Right? Some of them is a bit longer, some of them is a bit shorter. But they're also the moves. So you can see here, on March 1st, it looks like you have to look towards Aquarius. If your birthday is on March 1st, you probably know that astrology will tell you that. So we have the moves, but we also have there's a boundary in here that means that very deeply the Sun will actually be in the constellation of Polaris. It's not that the Sun suddenly moved, it's a put back. It's that when we defined the boundaries, the boundary of Ecliptic dips down in between Scorpio and Sagittarius. So now in that official boundary, it goes back. And here you can see, this is actually showing you, so this is Aquarius, here's Pisces, and Capricorn. This red line is where the Sun can go. Okay, this is where the Sun goes through here. Likewise here, this is Gemini, Taurus, and Cancer. You can see here that Orion actually comes right up here. It's really close to having the Sun actually go into Orion. Okay. So this is showing you where Ecliptic is. So this is Scorpio. The Sun follows a path that goes like this. It goes into Sagittarius, it goes into Scorpio. There's this little bit of Ecliptic. And so if your birthday happens to be at the right time, the Sun will be in that constellation when we go. Like I said, it's not that it suddenly changes its path. It always does that way. But we decided to define the edges of the constellation. So just for those of you that are actually curious, this is how it should be. So you can see here, I used to be Gemini and I am Taurus. Okay? And in fact, it used to be that the summer solstice on June 21st used to be basically the boundary between Gemini and Cancer. It is now at the boundary between Taurus and Gemini, which is moved by the constellation. Okay? If your birthday is at the beginning of December and you go to a Sagittarius, you are a Venus. Okay, and I'm actually going to leave you with this particular image because this kind of shows you where the constellations are. And this is where you can actually find out a lot of information. It's got all the maps, all the boundaries, and actually the history of how this came about. And this is the International Astronomical Union. And it's kind of
Okay, so I just did a little calculation here. You said 20 minutes times 4,000 years. By my calculation, that's 55 days. So nothing has changed that much.
It's actually almost changed by two constellations. It depends on, so the constellation boundaries are known, if you use those, so, let's back up a little bit. So if it used to be that the spring equinox was in Aries, and actually that kind of makes sense in terms of Aries as the total symbol and spring being about like spring, fall, and all that. And it's now in Pisces, but it's almost in Aquarius. It's actually moving the wrong way. But the boundaries mean that they're not all exactly 30 days. So some of them are more offset than others. Other questions?
Why is it a surprise?
It's not. This is something that anybody who has taken the intro astronomy class with me in the last 8 years knows that. I think my suspicion is that this is the sort of thing that gets discussed at meetings of amateur astronomy societies. And I suspect that there was one in Minnesota where somebody said this, somebody was deeply shocked and wrote an article, and the internet being what it is, it exploded into the blogosphere, and people like me had to write blogs. Other questions?